Hi, in the last video I showed you how to use the ULM generator to specify your own instruction set architecture so that you can build your own computer. And I just showed you with a few examples how you, for example, can define instructions for the ALU. In this video I want to uncover a few more details so that you can, for example, rebuild the features of the ALU project in Circuitverse on a larger scale. The ALU provided by the ULM generator has similar features to the ALU that you were building in Circuitverse. We just have larger registers. Each register can store 64 bits, and we have more of them. We have up to 256. Now, the reason to have this many registers is, of course, educational purpose. Then I can identify each register with 2 hex digits. It's actually kind of unrealistic to build hardware with this many registers, or the hardware would be kind of very expensive. But you're free to choose an instruction set where only 16 registers are used. Then you still have readable machine code. You can identify a register with 1 hex digit. So this is up to you. Besides that, the features that are similar to the ALU project in Circuitverse are also that we have a 0 register. That means reading from that register always gives you a 0-bit pattern, and writing to it has no effect. And for the operations, for the integer operations, we also have this well-known flex, and of course we're also using the 2's complement. You saw that the ULM generator provides some simple programming language that allows you to write this instruction set in this programming language, and it then generates from that the computer architecture. Here I will not describe formally the grammar, but you saw that you need to have to follow a certain structure, that you first have to define these formats that can be used in instructions, and after that you have this list of instructions that you describe. And here the grammar is basically that you first have at the beginning of a line some opcode, and this is followed by the format used for this opcode, and in the next line after some indent you have a block of C code. In most cases just one statement. And for defining your own instruction set, I have to uncover a few more details about how to write this implementation code, how to write this microcode, this thin glue between the instruction set architecture and the microarchitecture. For ALU operations, the ULM generator provides a C interface that you can use in the implementation of your instructions. Here I first want to point out some conventions that are used in this interface. For 64 bits, I'm using the type from the standard library for unsigned 64-bit integers, and this type will also be used for identifying registers. Although there 8 bits would be sufficient, but I will use the same type. This has the advantage that if you by accident, for example, would try to access the register with ID 257, I can detect that at runtime. So you get a runtime error and not just the result from the wrong register, or you don't by accident just write to the wrong register. And that's why I will use this type diff in the interface, so that you can see in the description of this functions, for example, for adding integers, that in certain parameters the ID of a register is expected, and in some other parameters a 64-bit pattern. For accessing information about the status registers, I have to identify the status registers. And for that I want to use readable integer literals. And I don't like macros, so that's why I'm using these enums. And with that you can access from this array of status flags whether a certain bit is set or not. Let me give you an idea why I think it's a good thing to use this type def. In the last video you saw how I implemented this instruction for adding 2 registers, and here you basically see the same implementation. In this implementation I'm using this regval function, which expects as parameter the ID of a register. So this ID always should fit into 8 bits. And here this always will be the case, because in the format I specified that X refers to certain 8 bits of the instruction. So you will always get a return value this 64-bit pattern stored in this register. Now assume that for some reason you change the implementation of this instruction into that, where you also add a 1. If I would use 8-bit integers, then, for example, calling this function with x equals 255, that means all bits are set, would result in 0 silently. That would mean the bit pattern of the 0 register gets used. Now the question is it this what you wanted, or is it something that you oversaw? And in my opinion, if you want to have this behavior that 255 plus 1 gets mapped to 0, then you should do something explicitly to make that clear. And otherwise it should be detectable as a mistake that you did in the definition of your instruction set. And so this will cause a runtime error. That means if somebody uses this instruction with x consisting just of this 1-bit pattern, it can be detected, for example, in a test. So it makes it possible to check your instruction set with a test suite. Let me review another example from the last video to explain this C interface. I was implementing instructions for initializing a register, a 64-bit register with 16 bits. And I needed 2 instructions for that because I wanted one instruction that applied a 0 extension to this 16 bits, and the other one should apply a sign extension. In both cases, I'm using this setReg function. And if you look at the interface, you see this function requires for identifying the register this ID which should fit into 8 bits, and for the bit pattern 64 bits. So in between, this extension needs to be done. And in the description of the format, it is defined how this extension will be done. In this first instruction with opcode hex 02, you specify that this should be a 0 extended bit pattern. And in this other instruction, you specify that a sign extension should take place. To make it possible that other people use your computer architecture for programming, you should provide them some nice documentation, not as technical as the explanations I gave you so far. And for that, we will use the notation introduced by Donald Knuth. So these last 2 instructions could be documented like that. That depending on the opcode, the effect would be that either a 0 extension gets applied to this bit pattern XY, or a sign extension. And with the extended bit pattern, the destination register gets overwritten. And I also can use this notation to give you homework assignments. For example, I could ask you to implement such an instruction where first this left shift is applied to the destination register, then the bit pattern of XY gets added and the result truncated to the 64 least significant bits, and with that the destination register gets overwritten. I can just state this assignment briefly like that. And the solution for that is actually quite easy. I just have to provide you a few informations about certain C operators that you can use, and in this case the solution would be as simple as that. And with the same notation I can describe the remaining functions of the ALU interface. You already saw in the ALU project how to describe the bit pattern computed by the adder. So with this notation I can describe what bit pattern gets stored in the destination register, and I also of course will specify what are the conditions for setting the different status flags. So for documenting your instruction set architecture, you just have to combine the documentation provided for the ALU with how you use this interface in your implementation of your instruction. So for adding registers, you would, for example, in this case, end up with a documentation like that. Now you, of course, can play around with this interface, define your own instructions, for example, for subtracting registers, multiplying registers, and so on.